Good evening, everyone. Welcome to Unacademy, India's largest e-learning platform, which is helping many students across the country to realize their dreams from all corners of the India, as well as from all branches of education system. It may be engineering, it may be medical, it may be IIT, it may be junior inter, it may be competitive exams, whatnot. Everything, everything. Unacademy is doing that. So thank you for all of you for joining me today in the evening session of uh, a subject called electronic devices. A subject called electronic devices. Yeah, this electronic devices will help the students of GATE and ESE, that is engineering service examination. This is lecture number 20, and today we are going to discuss about something called Zener Diode. Something called Zener Diode. Okay. Yeah. Myself, Shravan Kumar, having master's degree from JNUH in VLSS system design. VLSS system design. I have 10 plus years of teaching experience, and I can teach the subjects called EDC, that is electronic device and circuits, so which we are discussing right now. And we can also I can also teach analog electronics, which I am already teaching in Unacademy app, and I can also teach digital electronics and EMFT. So you can use a promo code of SVS10. You can use a promo code of SVS10 to get 10% discount on plus subscription. So what do you mean by a plus subscription? So what do you mean by a plus subscription? A plus subscription students will get a benefit of attending all the live classes. He can listen to all the crash courses which are available right now. You can write a weekly test. Sir, as I told you time and again, this is very important. GATE is not just about how you learn. GATE is all about how you practice and how you write the examination. You may be good at all the subject, but if and only if when you try to write the examination, then only you will know how much progress you have. Then you have something called a doubt solving session. You have a doubt solving session. For every 4th hour, it is going to be a doubt solving session. And you have English and Hindi. As a medium of communication, so which will help for both South and North Indian students. So we have something called rank improvement batch. Those students who are having some good basics in the subjects and they want to improve their rank, it will be useful for them. And we have something called iconic batch. So what is iconic is will find along with this plus benefits, a iconic batch students will get a benefit of personal coach. You'll have a study planner, you'll have a study booster sessions, and you'll have a personalized test analysis. You have a personalized test analysis, and you'll have a preparatory study material available, which is very much important. That is notes and practice sets. It's notes and practice sets. Good evening, Balaji. Good evening. Welcome. And a student who is having a plus subscription for 12 months need to pay 27,225 rupees. And SVS 10 is going to be a promo code. It's a 10%. You will get a discount as a promo code. And for a plus subscription having 18 months, you have a fees of 34,650 rupees. And you have this SVS 10 is going to be 10% discount you will get. And for 24 months, especially those who are in second year and third year, they can target for this 24 months. That is going to be 2023. Target 2023. This subscription will be useful. So that fees is going to be 39,600, and you are going to have SVS 10, and again you'll get a 10% discount on that. 10% discount on that. So this is going to be iconic. For iconic subscription, you need to pay 45,220 rupees for 12 months. So which having SVS 10 as a promo code and 66,600 as a fee for 24 months subscription, and you can use a SVS 10 as a promo code so that you'll get 10% discount. So how can you pay, sir? You can pay using EMI. We have an EMI facility. You can pay using credit card facility. and you have a wallet also. Wallets, you have a wallets also. All these things can be useful, right? You can pay with anything. You can pay with anything. Okay, yeah. So those who did not download, the Unacademy app, I would request you to download the Unacademy app. How will you download Unacademy app? It's very simple, sir. Simply search on Unacademy learning app. You'll get it, and you simply click on install. Vasu, good evening, Vasu. Good evening. Good evening. And you have a step number 4 is choosing your goal. Choosing your goal, you need to choose GATE and ESE as a GATE and ESE as your goal. GATE and ESE as your goal, because we have many other things also. You have NET exam, you have IIT JAM exam, you have NEET PG, for all these things. So I would request you to select this. So after that, you have the 3 types of classes: plus classes, free courses, and special courses. The plus special and free courses are free, and plus the subscription. So get subscription by click on it. Get subscription by click on it. Krishnaveni, good evening. Krishnaveni, good evening. Yeah, this is another new batch started on 20th of the December. Know your basics. Know your basics. So which is free for special class series. Free special class series. So targeting, actually this is targeting 2022 and 2023. So what we'll get here is, yeah, I'll take your doubts in the last. Balaji, I'll take your doubts in the last. So first let's move with what we are discussing. Surely I will take your doubts. I think you have already noted down your doubts. So I'll take all in the last. Is that fine? So this is a complete roadmap approach to each and every subject. Complete roadmap to each and every subject, and you have a subject-wise strategy to understand GATE 2022 to 2023, and then you have induction and guidance by India's top educators across all the branches. So for mechanical, civil, electrical, ECE, CSCIT, and chemical engineering, for everything, everything. Okay. So Ascent 2023, Ascent 2023 is the targeting the second year students, especially those who are preparing. So this batch starts on 21st of December, and it will be in English and Hindi. So this is for electrical engineering. They are the top faculty members of Unacademy, and you can use this EE Gate 10 as a promo code. Gate 10 as a promo code. And Ascent 2023 for ECE also we have. This also started on 21st of December, and classes will be in English and Hindi. These are top educators of Unacademy, and you can use ECE Gate 10, ECE Gate 10 as a promo code. ECE Gate 10 as a promo code. And we have Evolve 2022 targeting third year students, those who will attend next year GATE 2022. So this is also started on 21st of December. Again, the classes will be in English and Hindi. These are the top educators of Unacademy, and you can use same ECE Gate 10 code. And Evolve 2022 is targeting the students of third year, and this will be again started on 21st of December. Classes will be in English and Hindi. So these are the top educators. And this is going to be ECE Gate 10, doubly Gate 10 for that promo code. Yeah. Now you can follow me on Unacademy. Many times I have told you. So this is my user ID Z614A9LLPDQQ. Right. So I would request you to follow me on that. So we will discuss about actually Zener Diode. Before discussing Zener Diode, just recall what we discussed in the previous class. We have discussed something called diode capacitance in the last class. So how many types of PN junctions can be constructed? The 3 types of junctions can be constructed: alloy junction, grown junction, diffuser junction, right? So we have discussed about each one of them: alloy and step graded, or it also called as step graded junction. So how will we convert it, sir? It will be on one of the, see, we'll get one semiconductor. On one semiconductor, you will place a trivalent impurity and it will be heated. So now what happens, sir? This trivalent impedance will be diffused into the given semiconductor material. Then there exists something called a junction. So we name it as a PN junction. We name it as a PN junction. And we have seen grown or linearly graded junction. In this case, what we'll do, sir? We'll consider one silicon or germanium semiconductor, and on one side of the semiconductor will pour acceptors, and other side will pour donors. So again, there exists a junction. So how we diffuse junction? Diffuse junction is very simple. What we'll do is, sir, so you'll take one semiconductor material, and which will be now an n-type gas impurity will be blown onto it. So now what happens, sir? So these will be impurities will be diffused on it, and what happens, sir? You will find a p and n-type, and this is a p-n junction will be formed. CJO. We will see, Balaji. You just type your doubt, we'll see. So we have diode capacitances, we have diode capacitance, transition capacitance, diffusion capacitance. Now we have seen what is the capacitor also. So the diode at equilibrium, and when it is forward, we call diffusion capacitance, and then transition capacitance we have. At equilibrium, we have seen we got Cj naught, which is going to be a by 2 square root of 2 epsilon q into Na Nd by Na plus Nd into 1 by V naught, where V naught is going to be the barrier potential voltage. Now tell me, is that your doubt? Balaji? Cj naught is going to be a by 2 into square root of 2 epsilon q into Na Nd by Na plus Nd into 1 by V naught. Is what a Cj naught? Okay. So this is Cj is going to be forward bias is going to be Cj naught by 1 minus Vf by V naught. So here how we take 2 and inside 2. Hey, you're talking about this? It's very simple. So I'll write it here. I'm just trying to write when I'm a by 2 into 2 by square root 2 epsilon, I'm saying, right? So how can I write this? Can I write this as a by 2 into square root 2 into square root 2 by square root 2? So square root will get cancelled. I'm multiplying and dividing with 2. That's it. I'm multiplying and dividing with 2. What you'll get is, then simply you'll get a by 2. So what will be remaining? A by 2, and this denominator root 2 will go up. This denominator root 2 is going to be going up. The 2 in the denominator will go up. So you'll get 2 epsilon q into Na and dy. Did you get my point now? Is the point clear? Okay, okay. So we have seen this is going to be Cj is going to be Cj naught by 1 minus Vf by V naught power n, where n is equal to 1 by 2 for step graded junction and 1 by 3 for linear graded junction. And similarly, we have calculated CD. Diffusion capacitance is going to tau into di by dB, or we have derived CD is equal to tau I by eta Vt. 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 What we have discussed. And when it is the reverse bias, we have transition capacitance. The value of transition capacitance is nothing but Ct is equal to Cj by 1 plus Vr by V naught power n. This Vr represents the reverse saturation current, and once again n is equal to 1 by 2 for step graded junction, and n is equal to 1 by 3 for linear graded junction. And I think we have discussed some good number of problems. I think we have discussed some good number of problems. Now we will move on to the today's topic. Zener diode. So before going to study about Zener diode, we need to study a few things very importantly. They are called breakdown mechanisms in a diode. Breakdown mechanisms in a diode, right? Now we'll discuss in detail about this. So when a diode is reverse bias, for a small reverse voltage, then the diode current is small and almost constant, and it is equal to I naught. That is reverse saturation current. What is I naught? I naught stands for reverse saturation current. This I naught stands for reverse saturation current, right? But when the reverse voltage increases beyond certain value, large diode current flows. This is called breakdown of the diode, and corresponding voltage is called reverse breakdown voltage. Sir, so what is trying to say is here, so we have a current which is flowing, very small current is flowing, very small current is flowing, and we call this as I naught, reverse saturation current. Till some point of time it is okay. After it is crossing some voltage, after it is crossing some voltage, there will be sudden increase of the current. There will be sudden increase of the current, and this is because of something called breakdown. And this corresponding voltage is called V breakdown. V breakdown. So somebody it represents as VBD. So till this point, no problem. Till this point, no problem. A constant reverse this current is nothing but reverse saturation current. Reverse saturation current. Reverse saturation current. This is called reverse saturation current. So till this some point, reverse saturation current is constant. But after a point, a breakdown will occur. A breakdown will occur, and because of which there is a sudden increase of current. I'll explain you. Don't worry. I'll explain you why this breakdown will occur. Why this breakdown will occur? What makes this breakdown? What makes this breakdown? Right? You need not worry. But remember, there is a breakdown because of after crossing some voltage. This is all about in reverse bias, sir. This is going to be VR, reverse voltage, and this is going to be IR actually, reverse voltage, which will be in microamperes, and this is going to be in milliamperes. I forward current is going to be milliampere. This is a voltage. I can write minus VR also. Minus VR also. Okay, so after some point, what's happening, sir? There exists something called breakdown. There exists something called breakdown. So after the breakdown, there is a sudden increase of current. After there is a sudden increase of current. So what this breakdown is happening? How many types of breakdowns are there? What are the reasons behind this breakdown? What made this breakdown to come? Yeah, there are two distinct mechanisms due to which the breakdown may occur in the diode. They are called avalanche breakdown and Zener breakdown. Avalanche breakdown, Zener breakdown. So, sir, before we discuss about avalanche breakdown, what do you mean by avalanche, sir? Have you ever heard a word called avalanche? Have you ever heard a word called avalanche? What do you mean by avalanche? Tell me if you know. If you know what do you mean by avalanche? Have you ever heard what is avalanche? No, you did not. You did not heard. Are you listening? Are you listening for the first time? You did not heard. Okay, Balaji, no problem. Avalanche. Avalanche is generally used. This word is sudden flow of, sudden fall of, sudden fall of snow. Generally, avalanche is a word which is used for sudden fall of snow. In the extreme uh, parts of the globe, what happens, or even let's say as an Indians we can say, if you take at Mount Everest, there will be sudden fall of snow. In 1 second, in 1 minute, there will be a 100 feet snow will come up. There will be sudden fall of snow will be there. That is called avalanche. That is called avalanche. So what does it mean is there is a sudden fall. This word, you remember this sudden fall. You remember this word sudden fall. There exists something, the sudden fall. Due to the sudden fall, there is something called a breakdown. So the sudden fall of snow, is nothing but avalanche. That is now here this is called breakdown. So what is avalanche is avalanche of the charge carriers. Avalanche of the charge carriers is I am talking about. Charge carriers. It means what it means, sir? There will be sudden increase of the charge carriers. There will be sudden increase of charge carriers. That is called avalanche. So this all because of something called breakdown. This will happen because of something breakdown. There will be sudden increase of charge carriers. There will be sudden increase of the charge carriers because of something called breakdown. So we named it as avalanche breakdown. Avalanche breakdown. So Zener is the breakdown is. We will see what is Zener also. Zener is a scientist's name actually, right? So Zener breakdown. These two mechanisms, one is called avalanche breakdown mechanism and second one is called Zener breakdown mechanism. Now we will see what does it mean by avalanche breakdown mechanism. So the avalanche breakdown occurs in lightly doped diodes. Understand this word. Remember this word, lightly doped diodes. Lightly doped diodes. As the applied reverse bias voltage is increased, the velocity and hence the kinetic energy of a thermally generated charge carriers increases. If such charge carriers collide against one electron involved in the covalent bond, these collisions break its covalent bond and create new charge carriers. These secondary particles are also accelerated and participates in collision that generate new electron holes pairs. This phenomenon is called avalanche. See, so I'll explain it here very clearly. Let's say due to increase of current, due to increase of the temperature, some new electron has come. This electron is existing. Remember, this electron is existing. So now what happens, sir? Let us say I have some. So let's say I have some two or three electrons are present here. Do you think this free electron will sit silently? Do you think this free electron will sit silently? No. What it will do is it will try to go and hit the electron which is present in the covalent bond. When this is hitting the covalent bond, now what happens, sir? Because of this collision, this is nothing but collision. Because of this collision, this electron will come out. Of course, you will also get a hole. And this is which is already sitting silently. Do you think this is sit silently? No, this will also go and hit. Again. This will also go and hit another electron. So this is this. So again consider. So you have some 4 electrons. So this will again go and hit. Collide with this. Now which will again create another electron and hole. So this previous one is also going and hitting another one. So because of which another hole has come, another electron has come, another hole has come. Now what's happening? Again these two will go and hit. You will get another hole and holes. Now this again generate holes, electrons and holes. So now what's happening, sir? Slowly the number is multiplying. It is increasing. It is slowly increasing. So because of what? As the temperature increases, this free electron which has come is colliding with the electrons which are present in the covalent bonds, and this will make again a electron hole pair. So this electron hole pair will again multiply. So 1 will become 2, 2 will become 4, 4 will become 8, 8 will become 16, 16 will become 32, 32 will become 64, 64 will become 256, 256 will become 512, 512 will become 1024, 1024 will become 2048. So like this, there will be sudden increase of the electron which is 1 is increased to 2048, 2048 in no time, within no time, within no time, within no time. So now what's happening, sir? This is all happening because of the collisions. As temperature is increased, as temperature is increased, as temperature. Now what's happening, sir? It is multiplied by 2, 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 multiplied by 2. So because of increase in temperature, the free electrons will collide with the electrons present in the covalent bonds, and that will create next free electrons. So this process will be happening in nanoseconds of time, or in microseconds, or in picoseconds of time. So one electron is creating 2048. Like you can say, you may think that it will not end here. So you'll have still this 2048 may become 4096. This 4096 will again become something. So this keep on going. This keep on going. So this is all multiplication process. Multiplication process. One electron, by colliding with the electrons which are present in the covalent bond, will create electron hole space. Electron hole pairs. So slowly what's happening, sir? In this case, see, the breakdown is not happening because of the applied voltage. Just remember, there just because of Vastu, it is happening all because of increase in temperature. Increase in temperature, not because of what you are thinking. Right? It is not because of the applied voltage. It is not because of the applied voltage. So it is very clear here, you can see. So of course, see, of course, actually, as we are increasing the voltage, now this indirect voltage is increasing the thermal temperature. They are interlinked actually, but originally it is all because of the thermal generation. This is all happening because of the thermal generation. There may be an increase in the voltage, that's okay. There may be increase in the reverse voltage. Of course, there will be increase in the thermal voltage, but because of which what happens, sir? Because of which what happens, sir? The thermally generated charge carriers will increase, and these charge carriers will collide against the electrons involved in the covalent bonds. So this will complete. Now because of the break, they create a new charge carrier. This increased new charge carriers will create the secondary particles, and this secondary particle will accelerate and participate in collisions. So now what happens, sir? Process is completing. This process is multiplying, and this process is beautifully called as avalanche multiplication. Avalanche multiplication. So the word avalanche I used here because there is a sudden increase of the charge carriers. There will be sudden increase of the charge carriers. There will be a sudden increase of the charge carriers. So because of that, it is called avalanche breakdown. This is all called avalanche breakdown. So how will you calculate this avalanche multiplication? You have some formula here. So the multiplication factor due to the avalanche effect is nothing but m. We call it as m. M is equal to 1 by 1 minus v by vbd power n. vbd power n. vbd power n. vbd power n. So where m is a carrier multiplication factor. That is how many times the carriers are increasing. This m representing how many times it is multiplying. How many times it is multiplying. Okay. So now the m is carrier multiplication. The n, actually this is not capital N. This is supposed to be small n. This is supposed to be small n. I think that by mistake it has written. So this is going to be a small n. So this small n nothing but this small n is a empirical constant. For n-type silicon, it's going to be 4. For n-type silicon, it's going to be 4. For p-type silicon, it's going to be 2. Sir, can you tell me why this is 4 and 2? It's all because of the mobility of the charge carriers. For electrons, what are the charge carriers? For electrons, what are the charge carriers? Sorry, for n-type, what are the charge carriers? Yes, Balaji is one of the reason. Yes, Balaji is one of the reason. Okay, you're right. Yes, Balaji is one of the reason. That's it. But importantly, because of the kinetic energy which is gained, and because of that, a temperature increases. As the temperature is increasing, all this multiplication factor is happening. So for n-type, electrons are the majority charge carriers. For that, we will have n is equal to 4. For p-type, it is going to be 2. And where V is the applied reverse voltage. V is the applied reverse voltage. V is the applied reverse voltage. The breakdown is reverse breakdown voltage. Sir, you can very simply you see what is there here. What we have studied. So from this formula, what you can do is so here I am talking about till this point I can call this as a VR. Till this point I can call VR, but at this point that VR becomes VBD. This is VBD, yes or no? You can see here very simply. So I can write this is going to be VR. If you want, you can write VR, the reverse voltage which you are applied. So whenever VR becomes VBD, whenever VR is equal to VBD, now what happens, sir? What is the value of m? M is equal to 1 by 1 minus 1 by 1 power n. So that is going to be 1 by 1 minus 1. That becomes 1 by 0. This becomes 1 by 0. That implies it would be infinity. So this is suddenly increased. So whenever this VR becomes equal to VBD, now what's happening, sir? This ratio also becomes 1. So this is going to be 1 minus 1. 1 minus 1 is 0. M is going to be infinite. That represents that you will have infinite number of electrons are forming. Infinite number of electrons are forming. Okay. Good. Now, VBD is a breakdown voltage. Due to this avalanche effect, the junction is said to be breakdown and the current starts increasing rapidly. Now, the breakdown having reverse breakdown voltage greater than 6 volts shows the avalanche mechanism. So, understand this. The diode which is having breakdown voltage of 6 volts, breakdown voltage of more than greater than 6 volts just will have avalanche mechanism. So if it is less than 6, what happens, sir? That is Zener mechanism. So what is saying, sir? The breakdown voltage should be greater than 6 volts. The breakdown voltage VBR should be greater than 6 volts to happen avalanche mechanism or avalanche mechanism of breakdown. To get avalanche breakdown, your VBR should be greater than 6 volts. Your VBR should be greater than 6 volts. VBR should be greater than 6 volts. Now here comes the concept of Zener breakdown. Zener breakdown. So this Zener breakdown occurs in a heavily doped diodes. Sir, did you remember the first point which I mentioned? This is in lightly doped diodes. So avalanche breakdown will happen in lightly doped, whereas Zener breakdown happens in heavily doped. That means you should have a P plus and a N plus, P plus and N plus. The Zener breakdown occurs. The Zener breakdown occurs. The Zener breakdown occurs in heavily doped diodes. The Zener breakdown occurs in heavily doped diodes. Right? For heavily doped diodes, the depletion width is very small. See, understand what it is means. What it is means. So for heavily doped diodes, what is saying, sir? The depletion width is small. Why the depletion width is small, sir? Why the depletion width is small? Now you just understand. I'll create. Why it has to. Why the depletion width need to be very small? The point you need to understand. Without understanding that, you should not move forward. You should definitely understand that. So what he's saying, sir, he's saying this is heavily doped P plus. This is heavily doped N plus. Sir, when it is heavily doped, what happens, sir? More number of holes will be present here. More number of holes and more number of electrons will present here. So these holes, the free holes which are present in P region, and the electrons in the N region will try to push this, will try to push this width. This we assume that is going to be width of the depletion region. So because of that push, the new probably this you'll get. So this width is decreased. This width is decreased, yes or no? This new width is only this. Understood the point? Understood the point? Why this width is small? Why this width is small? Why this width is small? Because the heavily doped charge carriers will try to push the depletion region from two ends. So because of that, what happens, sir? The size of the depletion region will be small. The size of the depletion region will be small. Okay. Next. Under reverse bias conditions, the electric field across the depletion layer is very intense. Very intense. So breaking of covalent bonds due to the intense electric field across the narrow depletion region and generating large number of electrons is called Zener effect. Zener effect. What is saying, sir? Under reverse bias conditions, the electric field across the depletion layer is very intense. Is very intense. Right? So that breaking of covalent bonds due to the intense electric field across the narrow depletion region and generating large number of electrons is called Zener effect. Is called Zener effect. So what is saying, sir? So now what happened? Now what happened? As I told you, so this side you have positive, this side you have positive electrons, I mean positive ions you have, and you have negative charge here, negative charge here. Now, as it is heavily doped, the electric field here, the electric field will be very much intense when compared with a normal PN junction diode. When compared with a normal PN junction diode. Now, when this electric field is very intense, now what happens, sir? There's a possibility that this charge carrier will be attracted. This charge carrier will be attracted, and this charge carrier will be attracted by this. Now, what happens, sir? These charge carriers will, this electric field will take out the covalent bond, the charge carriers present in the covalent, let's say electrons. The electrons present in the covalent bond will come out. Now, because of this, now what happens, sir? As because of there is an attraction force, because of attraction force, there will be a rupture of the bonds. There will be a rupture of the bonds. The two covalent bonds will have a rupture. So when they are having rupture, as we know, when we rub our hands, the heat will produce, right? So similarly, when two covalent bonds are rubbing themselves because of the attraction, now what happens, sir? While this rupture is happening, the electrons will come out. The electrons will come out, or the charge carriers will come out. So now because of that, the more number of charge carriers will come. So this will happen only in heavily doped diodes. So now what inside? Because of very intense electric field, the breaking of the covalent bonds due to intense electric field across the narrow depletion region. We just now discussed why it is a narrow depletion region. And this generating the large number of electrons is called Zener effect. It's called Zener effect. The previous was avalanche effect. Now it is called Zener effect. So generated electrons constitute a very large current, and the mechanism is called Zener breakdown mechanism. Understand, remember one point very clearly. It all happened because of the rupture of the covalent bonds. Zener breakdown happens because of the rupture of the covalent bonds in a heavily doped diodes. In a normal diode or lightly doped diodes, this will not happen. And the advantage in Zener diode or Zener breakdown is nothing but the Zener breakdown happens because the uh, the both P and N regions are heavily doped, and the size of the width is very small. Right? Okay. And now you can see the diodes having reverse breakdown voltage less than 5 volts. Less than 5 volts shows Zener mechanism of breakdown. So for VBD, that is V breakdown voltage, which is less than 5 volts, the breakdown which happens because of the less volt, that is 5 volts, less than 5 volts, is called Zener breakdown mechanism. So, but what about avalanche? Avalanche is happening because of having breakdown more than 6 volts. If a diode has a breakdown of more than 6 volts, it is happening because of the avalanche. If it is happening if the breakdown is happening below the 5 volts, is because of Zener breakdown. Okay. Now, what happens to breakdowns with temperature? So the temperature dependence of a breakdown voltage. Temperature dependence of breakdown voltages. In a heavily doped diodes, the depletion region width is very small. That is what just now we discussed. Yes or no? The applied voltage produces an electric field which is very intense. In such a case, if the temperature increases, valence electrons acquire the higher energy levels, and it is easy for the applied voltage to push such electrons from covalent bonds to make them free. Thus, for small voltages at higher temperature breakdown occurs. So just try to understand what is saying. Already breakdown is occurring. Let's say the temperature is at, let's say I am having the temperature of 300 degrees Kelvin. 300 degrees Kelvin, and the V breakdown is going to be, let's say, 5 volts. Right? So now I am increasing the temperature of T is going to be, let's say, the temperature of 310 degrees Kelvin. Now, what is saying, sir? We need a breakdown voltage. This is, let's say, VBD1, let's T1, T2. This VBD2 should be less than VBD1. It means breakdown occurs before the VBD1. It means breakdown occurs breakdown occurs before VBD1 it only. Why, sir? Why, sir? As we discussed, already some external electric field is created. External electric field is created because of the reverse bias voltage already. But along with this, I am trying to improve the temperature. I am trying to add this extra one. I am trying to add this extra one. When I am trying to add this extra one, now what happens, sir? The breakdown occurs before this. Let's say it may occur at 4.8 only, 4.8 volts only. It 4.8 volts. Sir. That means let's say initially the breakdown was occurring at this point. Let's say the 5 volts, 5 volts. This new breakdown, this new breakdown this new breakdown will occur. So before that itself, and this, let's say, assume it's going to be 4.8 volts. I think the point is clear for all of you. I think the point is very clear for all of you. So the breakdown occurs before as the temperature increases. So at temperature T2 it is going to be 1. This at temperature T1 you are going to have the 5 volts. You are going to have 5 volts. And you'll get only, I'm taking it as an examples. I'm taking it as an example, not exactly what I'm saying. Right? Not exactly what I'm saying. Not exactly these values. But this is going to happen. This is going to happen. Is the point clear? Are you all there? Are you getting bored of it? Is it boring for you? Is the class boring? No, right? You're talking about this? You're talking about this? So I'll wait. I'll try to explain you very clearly. Right? So assume that at T is equal to 300 degrees Kelvin, the breakdown is happening at VB1. VB1, it is at 5 volts. So it means the breakdown voltage, let's say the breakdown voltage is this. This is the breakdown voltage. So what is the voltage? Let's say 5 volts the breakdown is happening. 5 volts the breakdown is happening. 5 volts the breakdown is happening. Now I increase the temperature to 310 degrees Kelvin. So I increased by 10 volts. I am increasing by 10 degrees centigrade. Now what happens here is the breakdown is occurring before that. It means the new breakdown will not happen at 5 volts, but the new breakdown will happen at 4.8 volts only. You don't need 5 volts to make this breakdown. This is going to be VBD1. This is going to be VBD2. Is the point clear, Balaji? Is the point clear? Is the point clear? So earlier the breakdown used to happen at 5 volts. Now the breakdown is happening at 4.8 volts only. 4.8 volts only. Okay. Good that you are learning new points, Vasu. So thus the breakdown voltage decreases as the temperature increases. The breakdown voltage increases as the breakdown voltage decreases, the temperature increases. This is because of the breakdown. The Zener breakdown has negative temperature coefficient. Negative temperature coefficient. Negative temperature coefficient. In lightly doped diodes, the width of depletion region is large and the field intensity is low. So the breakdown possibility is because of the avalanche effect. So he's talking about a lightly doped. This is all The Zener breakdown is happening in a heavily doped diodes. In a heavily doped diodes. But here, in this case, it is not happening because in a lightly doped diodes. So it is not happening because of the field intensity. So if you remember how the Zener breakdown is happening, sir, the Zener breakdown is happening because of the electric field which is created inside, and that electric field, because of that electric field, the covalent bonds are breaking. The covalent bonds are breaking. That intensified electric field will not be present in a lightly doped diodes. So, now what happens, sir? In a lightly doped diodes, the breakdown occurs because of the avalanche effect. Because of the avalanche effect, not because of it means because of the collisions. Because of the collisions. But blindly remember, avalanche effect is because of the collisions, and the Zener breakdown is because of rupture. Because of the rupture. Because of the rupture of the covalent bonds. Because of the rupture of the covalent bonds. In such a case, if the temperature increases, the vibration of the atoms in a crystal increases. The intrinsic holes and electrons have less opportunity to impact sufficient energy between the collisions due to vibrations. So to start the carrier multiplication, thus the voltage must be increased to cause a breakdown. So at higher temperature, sir, is talking. This is all talking about avalanche. This point belongs to avalanche mechanism. So this point belongs to avalanche mechanism. So avalanche mechanism has a positive temperature coefficient. It means so you may think that if the temperature increases, now the multiplication of charge carrier is happening. But now what happens, sir? As the temperature is increasing, there will be a chance that the collisions will start decreasing because of the more vibrations. As the more vibrations are happening, there will be less chance for this to. So as it is moving like this, so the electron which is coming may not hit directly. So earlier when it was coming, you can hit directly, because of which the covalent bond may break. But it is now moving. So it is moving. So when it is moving, what happens, sir? There is a less chance of collision. There is less chance of collision. So as the temperature increases, the vibrations will increase. The vibrations will increase. The vibrations is increasing. There is a less chance for hitting. Less chance of hitting. So now avalanche mechanism will not happen very quickly when compared with the previous case. So you need more breakdown voltage. So in case of this, all happens in case of a lightly doped diodes. Okay. Thus, voltage must be increased to cause the breakdown. So at higher temperature, high breakdown voltage is necessary. At higher temperature, a high breakdown voltage is necessary. Thus, breakdown voltage increases as the temperature increases for the avalanche breakdown. The avalanche breakdown has a positive temperature coefficient. So Zener has negative temperature coefficient, and this avalanche has a positive temperature coefficient. Okay, Zener needs negative temperature coefficient, and avalanche needs positive temperature coefficient. So now you can see here, if this voltage is 6 volts, you can have this. So this is 5 volts. So below 5 volts, Zener breakdown will happen. Above 6 volts, avalanche breakdown will happen. So this is a heavily doped PN junction. We're talking about a heavily doped. We are talking about heavily doped. We are not much bothered about the forward bias characteristics. We are very much bothered about the reverse bias characteristics here. So do you think this is important? This is important, very much important. This reverse bias is very much important. You will see the best advantage of this in today's class itself. We think that this is the disadvantage, but no, this is the best advantage of a heavily doped PN junction diode. You know what happened is, for a sudden rise of current, let's say current was, let's say here 10 microamperes. So even for 100 microamperes, or 1000 microamperes, what happens, sir? This breakdown voltage is constant, 6 volts only. So for change in current, you have constant voltage. For a constant, you have voltage is constant. Don't think that reverse bias is waste. No, sir. This reverse bias has the best advantage. Many people think that there is no use of reverse bias, but reverse bias has the best advantage. So for this change in current, your output voltage is constant. Let's say 5 volts. Irrespective of the change in current, still you will get constant voltage. So what is this called, sir? If the voltage you are getting is constant, even for the change in the voltage current, change in the current, for change in the current also, your output is constant. What does it mean? Is it not advantage? Yes, it is advantage. We will discuss this advantage in detail. It means we will call a regulated output. Irrespective of change in current, you got some constant value, some constant V0, constant voltage. Very good advantage of this. Very good advantage. Okay, now we'll move on. Now here comes Zener diode. Of course, this Zener diode must be definitely a heavily doped diode. Zener diode must be a heavily doped diode and is designed with adequate power dissipation capabilities to operate in reverse breakdown region. So it has very good power dissipation capabilities, right? To operate in a reverse breakdown region. So the Zener diode, the best use of Zener diode happens when it is reverse bias and when it is operated in breakdown region. So there is no use of the Zener diode if you operate in this region of forward bias or reverse bias also. When this the best advantage of this Zener diode is when you use this in a breakdown only. When you use this in a breakdown only. So the operation of Zener diode is same as that of the ordinary PN junction diode under forward bias. That's what I told you. So the Zener diode forward bias characteristics are same as that of a normal PN junction diode. The normal PN junction diode, but it changes. So ordinary PN junction under forward bias conditions, no need to worry, very easy. In reverse bias condition, the diode carries reverse saturation current that we know till the reverse voltage applied is less than the reverse breakdown voltage. So he is talking about this point. Till this point, what you have, sir? You have a constant I0. Let's say some voltage is VR. Till this point, you are talking about VR. Some voltage VR, right? Till this point. So what is saying? Till this point. So till the reverse voltage is less than the breakdown voltage, you'll have a reverse saturation current I0. So when the reverse voltage exceeds the reverse breakdown voltage, the current through it changes drastically, but the voltage across it remains almost constant, such a breakdown region is a normal operation region in a normal operating region of the Zener diode. This is a normal operating. I think this is repeated. Such a breakdown region is a normal operating region of a Zener diode. So we should operate this Zener diode. We should operate this Zener diode in this breakdown voltage only. This is a breakdown region. Should call as a breakdown region. I should call this as a breakdown region. This is called a breakdown region. This is called a breakdown region. Right? So the best advantage of Zener diode is when it is operated in it's a breakdown region. No use of operating the Zener diode before breakdown and in the forward bias also. The forward bias is as same as normal PN junction diode. But when it is reverse bias also, up to till some point before breakdown, there is no use of this because you will get a constant current I0. But the best advantage of a Zener diode is when it is used in the breakdown region. That is the voltage which is greater than VBR, breakdown voltage which is greater than VBR, which is greater than VBR. So now we will see the symbol of Zener breakdown is this. You can see in a Zener diode symbol you can see a Z. This is Z or not? This is Z or not? Yes or no? Anode and cathode. So you need not worry. Zener in the Zener diode symbol you will find a Z. The Zener symbol you will find a Z. You will find a Z. Sir, if it is tunnel diode, I'm talking advancedly on tunnel diode, tunnel diode, tunnel diode. Tunnel diode should have a T. That's it. I'm just trying to make you comfortable to remember. Is this T or not? Is this T or not? So if it is tunnel diode, the symbol contains T. If it is Zener diode, the symbol contains Z. The symbol contains Z. If tunnel diode, the symbol contains T. That's it. Very simple. Very simple. You will not get confused. You will not get confused. Right? This is how you can simply remember. You can simply remember. Okay. Next. So the dynamic resistance of Zener diode is defined as the reciprocal of slope of the reverse characteristics in a Zener diode. So that is nothing but delta Vz by delta Iz. Delta Vz. So it is nothing but the slope of the reverse characteristics in a Zener diode. Slope of the reverse characteristics. So we have seen what is the reverse characteristic. This is what is equal to y is equal to mx. Y is equal to mx. Slope is going to be m is equal to y by x. Y by x. On x-axis, what you have, sir? Current. On x-axis, you have current. On and y-axis, you have current. On x-axis, you have v. So it's going to be delta v by delta I by delta v. Delta I by delta v is going to be the slope. Delta I by delta v is going to be the slope. But if you want to calculate, the dynamic resistance, is called dynamic resistance. So 1 by slope. So what's nothing but 1 by, so the slope was delta I by delta z or delta Vz, delta Iz by Vz. So I can say it's going to be delta Vz by delta Iz. So please give the comparison of avalanche and Zener construction, working and slope diagram. See, the avalanche will happen. The avalanche will happen. So major difference is this only. Major difference is Zener breakdown happens in heavily doped diodes. Okay, heavily doped diodes, heavily doped diodes. Whereas the normal avalanche breakdown happens in breakdown happens in lightly doped. Lightly doped. First difference is it happens because of the lightly doped diodes. Avalanche breakout mechanism happens in a lightly doped diodes. Zener breakdown happens in heavily doped diodes. And avalanche breakdown voltage will be greater than 6 volts. Avalanche breakdown voltage is going to be greater than 6 volts. Avalanche Zener breakdown voltage is going to be less than 5 volts. Less than 5 volts. So working you already know. There's nothing but there's no avalanche diode. Avalanche diode is nothing but normal p-n junction diode only. Normal p-n junction diode only. Right? So you have their multiplication, and here this happens because of avalanche breakdown. Happens because of the, as I told you, avalanche happens because of the collisions. Avalanche breakdown happens because of collisions, whereas Zener breakdown happens because of the rupture of the covalent bonds. Rupture of the covalent bonds. And avalanche breakdown has a positive temperature coefficient. So if you want to write, you can write all these things. Avalanche Zener. It happens in a normal p-n junction diode, normal doping or lightly doped, or you can call as lightly doped here, and this is heavily doped. This is in heavily doped, and this is VBR is greater than 6 volts, and here breakdown voltage I'm talking about. VBR is going to be less than 5 volts. This is having positive temperature coefficient. Positive temperature coefficient. And this is having negative temperature coefficient. Negative temperature coefficient. And what else remaining, sir? This is positive temperature coefficient. This is negative temperature coefficient. So you will have a breakdown we have discussed. And this is because of collisions. Avalanche breakdown is because of the collisions, and this is because of rupture of covalent bonds. Okay, so this is what all about avalanche and Zener breakdown mechanisms. So the dynamic resistance is very small. It is the order of a few tens of ohms. So now equivalent circuit diagram of a Zener diode. This is Zener diode. So practical equivalent circuit is going to be, you are going to have a resistor RZ in series with this VZ. So remember this Zener diode must be always used in reverse bias, that too in breakdown region only. So when it is a breakdown, what happens, sir? You can see here, you'll have a positive VZ. So practical equivalent circuit. So you can see here, you have a positive VZ. Don't get confused. Generally, here you'll have anode and here you'll have a cathode, right? Anode and cathode, but it is cathode side, you will have a positive voltage. Anode side, you will have a negative voltage. This all because it is in the reverse bias. This should operate in only reverse bias. The best advantage Zener diode will happen only when it is in reverse bias. when it is in reverse bias. So remember, it will be positive and negative. If it is a normal PN junction diode, you will draw this positive and negative, positive and negative, is positive and negative, but it is reverse because the Zener diode is operating in reverse bias. When it is reverse bias, obviously you will have a negative here, well positive here, negative and positive. So if you consider its resistance also, it will become RZ. If you consider its resistance also, it will become RZ. If you neglect this, so you will have only the voltage VZ. You will have only the VZ. So that's the ideal equivalent circuit. So it's a practical equivalent circuit. This is ideal equivalent circuit. Ideal equivalent circuit. Okay. Next, what are the applications of a Zener diode? What are the applications of a Zener diode? So the various applications of Zener diode are, it uses as a voltage regulating element in voltage regulator. This is what I was talking about. A Zener diode will be used as a voltage regulator. In various protecting circuits. So this Zener diode must be used as a protecting element. Zener diode used as a protecting element, right? So it used as a Zener limiter, that is clipping circuits. I think we have discussed about this Zener clippers, clipping using Zener diodes, clipping using Zener diodes also we have discussed in analog electronics in app. In the app we use this. So in Zener limiter, that is clipping circuits which are used to clip off the unwanted portion of the voltage waveform. So these are the advantages of application. These are the applications of Zener diode. It can be used as a voltage regulator in protecting elements, and then limiters. These are the different applications of a Zener diode. Now here comes the concept of voltage regulator. Which circuits are called as voltage regulators? So which circuits are called as voltage regulators? A voltage regulator is an electronic device which produces constant output irrespective of the variations in the input voltage. Very remember. So constant output in variations in the input voltage and load variations. So why do we need this? I'll tell you. Let us say you have some circuit here. You have some circuit, some power supply. Let's say some power supply. I'll use this power supply concept. Let's say you have some power supply. And you connected it to, let's say a mobile charger you are connected. Or you have connected a TV. You can connect some laptop. These are the electronic devices, or no? These are the electronic devices. These are different electronic devices which you have. This is a power supply. Let us say, so what is saying, sir? It should give a constant output voltage. Variation in the input voltage and load variations. So you should get a constant voltage. Let's say initially you got 230 volts. So because of some power fluctuations, let's say you got only 220 volts. So this power supply should give me only 5 volts, let us say. Of course, in between you will use an adapter, sir. Adapter for this, because it's going to be 5 volts, it's going to be 12 volts, it's going to be 20 volts. Let's say example I'm telling you. This is 20 volts, here it's going to be 12 volts in general, it's going to be 12 volts. So I should get a constant output. Maybe let's say 15 volts I'm getting. No problem. Let's say I'm getting only 20 volts here. So this, irrespective of the variations, irrespective of the input variations, I should get 20 volts only. So the input fluctuations, because some fluctuations, you may get 210 volts only. I'm telling example, sir. I'm telling very examples. So it may not give 210 volts. So irrespective of change in input voltage, irrespective of change in the load, irrespective of the change in the load, I should get a constant output. So this is called a regulator circuit. That too also called voltage. Voltage regulator. Voltage regulator. It may not be power supply I'm talking about. It may not be power supply. So you may get some, it may not be power supply. Always power supply means it's not a battery. Battery is also a part of power supply. Battery can be a power supply. Yes, battery can be a power supply. Battery can be a power supply. Battery can be a power supply. Right? This device. If you think that, let's say this device, this device, which gets different input voltages, but it will give a constant output voltage. Let's say example 20 volts. This 20 volts should not change because of the load which you are connecting. Load what you are connecting. Load which you are connecting. Okay. The load which you are connecting. So because this mobile chargers, TV, laptops may be different. So if you are changing this load, this output should not change. Still you need to get 20 volts. So I'm not talking about the adapters. For different, but different you will have again different adapters. They are called rectifiers. Again I'll talk about this later. I'll talk about this later. In electrons we'll talk about this. But I'm talking about only the regulator here. I'm talking about only the regulator here. Okay. The voltage regulator is an electronic circuit. Is an electronic circuit that produces a stable DC voltage independent of the load current, temperature, and AC line volt variations. So what are talking about, sir? It is irrespective of load current, temperature, and input variations. I can call this as the line variation, means input variation. Line voltage variation. Line voltage means what voltage you are getting from the transformer to your home. Yes, we can have a Zener diode. Yes, we can have a Zener diode. Mahendra. Yes, that is what I am talking about here. You come to the correct point, Mahendra. You come to the correct point now. You have landed in this correct place. You have landed in the correct place. So this voltage regulator. Now we'll discuss about in the coming slides also we'll discuss how a Zener diode acts as a voltage regulator. How a Zener diode acts as a voltage regulator. We will discuss that point. We'll discuss that point. Okay, a voltage regulator is an electronic circuit that produces stable output, constant output DC voltage, independent of variations in the load current IL, temperature, and AC line voltages. If really want to change the input voltage, then what about output, sir? So what output, madam? Krishnavani, can you elaborate your question? So what doubt you have? What doubt you have? Why you want to change input? Whether you want to change input here or input here? What do you mean by input means? Input means is 5 volts, 20 volts, to 12 volts, or this 230 volts. What do you mean by input? Input of a regulator. Yes. Why do you want to change the input? See, the regulator is a device. The regulator is a device without worrying about the input voltage. It means not input means the fluctuations in the input, madam. Fluctuations. Generally, what happens, sir? You will see a lot of fluctuations will happen. Lot of fluctuation will happen, yes or no? You can see the tube light. You can see the tube light or some light. So light will come and go, come and go, come and go. Why, sir? Because of the input fluctuations. Input fluctuations. So why this voltage regulator is required? If you, let's say you are connected a 230 volts AC voltage to your TV. This is completely changing. This is complete. Let's say regulator is not there. Now what happens to your TV? Someday your TV will burn out because 1 minute you got 230 volts, next minute you got 12 volts, next minute you may get some 220 volts. So there is a fluctuation in the input voltage. If I'm directly connecting this TV to the fluctuating power supply, what happens, sir? This TV, laptop, mobile, whatever you are connected, that will burn. Power supply gives constant output. No. You may not give. See. The power supply, depending on, let's say that's again another topic called rectifier. You will have here rectifier here. Definitely, you this power supply will give you a constant voltage only. This constant voltage only. So that constant voltage, let's say you will get 230 volts, 230 volts AC. From this 230 volts AC, you may need for mobile phone you need only 5 volts. For TV you need 20 volts. For laptop you need 12 volts like this. So for all these things, you will get some constant voltage only, but you will have an adapter. You will have an adapter which will convert this 20 volts to 5 volts, 20 volts, 20 volts, 20 volts to 12 volts. Altogether different story. For different devices, obviously you need different voltages. For different devices, you need definitely a different voltages. Okay. Now, the factors that are determining stability, the output voltage V naught depends on the input unregulated DC voltage Vi, load current IL, and temperature T. Hence, the change in output voltage of the power supply can be expressed as this change in output voltage, change in output voltage, change in output voltage change in output voltage is because of three things. It may change because of the input change. It may change because of the load current. It may change because of the temperature. So what I am writing is dou V naught by dou Vi into delta Vi plus dou V naught by dou IL into delta IL, dou V naught by dou T into delta T. So as the output depends on unregulated input DC, that load current IL and temperature. So if you want to make this delta V naught, that is change in output voltage 0, all this delta Vi in, delta V, delta IL, delta T should be 0. When delta T, delta IL, delta V in is 0, then delta V naught is 0. What do you mean by delta V naught 0? Delta V naught 0 means you get constant output. You get constant output. You get constant output, which is very important. You get constant output. Okay. So this depends on change in input voltage, change in current, change in temperature. Yeah. So delta V naught, I'm just writing this as a coefficients, right? So SV, R naught, and ST are the coefficient, right? So where the three coefficients are defined, this delta V naught is going to be input regulation factor, that is SV is equal to change in V naught by change in Vi. Change in V naught by change in Vi. Change in V naught by change in Vi. I think here something went wrong. I think this is your change in IL. Consider this as a change in IL, assuming delta IL is equal to 0. Some print mistake happened. This print mistake happened. The change in output voltage because of change in input voltage. Change in output voltage because of the change in input voltage. Assuming change in load current is 0 and change in temperature is 0. Change in load current is 0 and change in temperature is equal to 0. Because three factors are there now. So what is the output resistance R0 is going to be change in output voltage with respect to change in output current. Change in output current by assuming change in V input is equal to 0 and change in temperature is equal to 0. And we call temperature coefficient. Temperature coefficient. What is temperature coefficient? Delta V naught by delta T. Delta V naught by delta T. That is delta V in is equal to 0 and delta L is equal to 0. Delta L is equal to 0. Smaller the value of the three coefficients, better the regulator power supply. So all this SV R naught ST is required to be 0, as low as possible. As low as possible. Then only what happens, sir? This change in V naught becomes 0 or very close to 0. So when this change in V naught is equal to 0, it means we get a constant output. We get a constant output. We get a constant output. Okay. What is load regulation? Load regulation is nothing but no load, V no load minus V full load by V no load, or V no load minus V full load by V full load. So majorly we'll use this one, V no load minus V full load by V full load only. So where V no load is the output voltage at zero load current, and V full load is the output voltage at related load current. This is usually denoted in percentage. So what is V no load? Understand here what does it mean? V no load is the output voltage at zero load current. What do you mean by zero load current? What do you mean by zero load current? IL is equal to 0 means what? IL is equal to 0 means what? The load is infinite. RL value should be infinite. Understand? Remember this. No load current. This no load means V no load means V no load current. V no load current means this IL should be equal to 0. IL should be load 0 means R naught should be infinite, as high as possible. As high as possible. IL should be as high as possible. V full load means IL should be infinity or related load current. So R naught should not be equal to infinity. Okay, V no load. Remember, no load current voltage. No load current. Don't think that load means that resistance. So you should read. Remember, V no load current. Right? So voltage at no load current. Voltage at no load current. Voltage at no load current. Voltage at full load current. Voltage at full load current. Full load current means IL should be as high as possible. IL should be as high as possible. IL should be as high as possible. Is the point clear? Is the point clear for all of you? Is the point clear, all of you? Okay. If R naught is equal to 0, there will be flow of current. Yeah, there is no resistance at all, right? Obviously, it's short circuit. Short circuit, Mahendra. When short circuit is there, high current will flow. High current will flow. High current will flow. That's it. High current will flow. That's it. Okay. Okay, we'll move on. Now, here comes Zener diode as a voltage regulator. The best application of a Zener diode. Best application of a Zener diode. Zener diode as a voltage regulator. Zener diode as a voltage regulator. So, you can see this diagram where the Zener voltage regulator is shown in the above figure, in which Zener diode is connected in parallel to load resistance RL. Is talking about this. This load resistance RL and Zener are in parallel. Both of them are in parallel. They are in parallel, right? The resistance RS is a current limiting resistor. It is called current limiting resistor. So, or you can protect this Zener diode. You can use this resistor RS. So, current limiting means it is trying to decrease the current. It is trying to decrease the current such that this load will not be affected. There will not be less effect on load for increasing the current. So, I should use this RS for current limiting resistor. I can call this as a current limiting resistor. Current limiting resistor. So, I think, are you able to see it now? Okay. This is a voltage regulator. So, you can see this is connected in reverse bias. This is connected in reverse bias. So, here we need to see what will happen. What will happen? The operation of this voltage regulator. The operation of this voltage regulator. Now we will see what happens. This is the VZ represents the breakdown voltage. VZ represents the breakdown voltage. VZ represents the breakdown voltage. Let us say this V input is greater than VZ. This V input is greater than or equal to VZ. Then what happens, sir? This VZ will be this Zener will be on. When the Zener will be on, what is the output voltage? I'll try to for V input greater than or equal to VZ, greater than or equal to VZ. Then now what happens, sir? Then Zener will be on. So the Zener is on. Now what circuit looks like, sir? The circuit looks like it gives a constant voltage. It gives a constant voltage. It gives a constant voltage. So what is that V output voltage? So V output is going to be VZ only. VZ only. This is plus minus VZ. VZ only. If a V input is less than VZ, then the Zener will be off. Zener will be off. So it means how the circuit looks like, sir. So this is open circuit. What its corresponding output? This is open circuit, sir. Open circuit. So what is going to be V naught? So then you need to calculate. So what is the voltage drop across this R? What is the V input voltage? What is the V input voltage? But whenever the Zener diode is operating in this breakdown region, it acts as a load voltage of VZ. So output will be always VZ. Output will be always VZ. Now, why Zener diode not acts as a regulator? As regulator when it is connected in series. So what do you mean by in series? Still it acts as a, see if you want to take the advantage, you are talking about this. You're talking about this. You're talking about in series, right? You're talking about this. Krishnavani, you're talking about this, right? This is R. This is some VZ it has, right? Remember Krishnaveni, whenever this input voltage is changing, of this VZ is constant. Yes, you are right. Input is changing, but VZ is constant. But will the voltage will be same? No. This is constant. Only this is constant. But this voltage will not be constant. What we need a constant voltage VZ. We need a constant voltage. We need is a constant voltage. So now, if it is connected in series, now what happens, sir? Now what happens? If you try to draw the equivalent circuit, some V input you are giving here. So it will be plus minus, and you will get this is output voltage. This is going to be VR. This is going to be R naught. It will be R naught, and this is going to be V naught. The voltage is here. This voltage is here. This is going to be some VZ. So if you apply KVL, V naught is not simply VZ. V naught is not simply VZ. V naught is going to be VI minus VZ. VI minus VZ. So however voltage changes, this output also changes. But what is required, sir? We required only constant output. So then what you need to do, sir? You need to connect in shunt only. Correct. It is useless in connecting. Yes, Balaji, you're right. Vasu, you said Zener diode when will act as open circuit. That's now I'm doing, right? So whenever V input is less than VZ, this acts as an open circuit. You will understand when I do some problems. We'll do one or two problems. On this Zener diode. Then you will definitely understand what I mean. You will definitely understand what I mean, Mr. Vasu. Okay. Now, when can it acts as a regulator? Now we will see. We have, let's say, V input is fixed and RL is also fixed. When V input is fixed and RL is fixed, now what happens? Let's say this is going to be case 1. Consider this as a case 1. Case 1. Now we will see. So what we will try to draw the circuit. I try to draw a circuit. Just pay attention. I'm just trying to draw this. And you'll have a V naught. So what he's saying, sir, is saying this RL, let's say low resistance RL. Since both V in and RL are fixed, and both V and RL are fixed, what is I? I is going to be IZ. This is going to be IL, load current IL. So what we know, sir? What we know, I is equal to IZ plus IL. IZ plus IL. IZ plus IL. IZ plus IL. So how will you calculate the value of V naught? V naught is going to be simply IL into RL. V naught is going to be simply IL into RL. V naught is going to be simply IL into RL. So how will you calculate it? So let's say first case 1. In this case 1, now if V is less than VZ, V is less than VZ, when this V input is less than VZ, for any voltage, which is less than Vz. So this is Zener diode is going to be off. Understood? For any voltage which is less than V volts, let's say for you to make understand Vasu, let's say this Zener diode is having a breakdown voltage of 5 volts. Breakdown voltage of 5 volts. For any voltage below 5 volts, this acts as a off. Let's say you are applying 6 volts, then this is 6 volts, this is acts as an on circuit. Okay, so any voltage which is less than Vz, that is, let's say 5 volts, this Zener diode acts as an off. Acts as an off. Acts as an off. So now when it is off, now what happens, sir? The current Iz should be 0. When the current Iz is equal to 0, so what is Iz is equal to I0 plus IL. So the load current IL, this implies load current IL is equal to I. Then what is the load RL? What is the voltage across that? What is that across that going to be? I into R. So let me draw this equivalent circuit. This is some resistance R. This is some input Vi. This is going to be R naught. Let's say it's going to be V naught is the voltage drop across this. So this current is same. Same current which is flowing here, same current will flow in IL only. Yes or no? So same, because there is no current flow, because the Zener diode is off. Zener diode is off. The Zener diode is open circuited. This current IL is going to be I same. Both of them are same. So load V naught is going to be I into R. Or I can also say this is going to be simply, let's say this is going to be the voltage V. This is going to be voltage V. It's going to be Vi minus V. This is going to be some voltage. You have plus and minus Vi minus V. So it means so what you are going to have is the current via the load resistance RL is going to be Vi minus V, and its corresponding current you can still calculate this current as VR by R. That is nothing but Vi minus V by R. Vi minus V by R. Vi minus V by R, the current flowing. That is same as this. So then what is PZ? The power dissipation across the diode. So Zener junction is going to be, Zener diode is going to be Iz into Rz. As already Iz is 0, so it's going to be 0 into Rz. So PZ is going to be 0. Z is going to be 0. So these are very simple, sir. Don't think that I am doing something extraordinary. No, all these things are very simple. I'm just applying KVL and trying to find out. Apply KVL, you get Vi minus V. Minus of plus Vi minus V. Plus Vi minus V is going to be V naught. And just I applied just KVL here. V naught. Is the point clear? Okay. Now in the case 2, so if V is input is greater than or equal to Vz, so here Zener will be on. Zener will be on. That is, now when it is on, it acts as a power supply of Vz voltage. It acts as a Vz voltage. Now here we have a load resistance RL, and here you have V input is going to be resistor R. So now what is going to be R naught? Sorry, what is going to be R naught? So what is going to be load value of the V output? Simply it's going to be V R. The load resistance R is going to be Vi minus Vz. Why, sir? Because you have Vz here. Because Vz you are having here. Then what is I? Now I is equal to Iz my plus IL. This is going to be I. I is going to be Iz plus IL. That is Zener current plus Zener current plus load current IL. Load current IL. So if you want to find out what is I, sir, you will understand all these things when you do some problems. Don't worry. We'll definitely do some problems in tomorrow's class. Today we'll finish off almost all the theory and we'll continue problems tomorrow. So you need not worry. So I is going to be again, the current is going to be VR by R. So I is going to be here VI minus VZ by R. VI minus VZ by R. VI minus VZ by R. Then what is IZ? The Z is nothing but simply I am changing from I minus IL. What I'm trying to do, I'm just trying to write all this things. Iz minus IL. Iz minus Iz is equal to I minus IL. I minus IL. So don't worry, we will discuss every point in detail. We'll discuss every point in detail. You will not worry. You will not worry. Right? I'll clarify your doubts also. Okay, next. Next, what is this? Let's say fixed VI and variable RL. Fixed VI and variable RL. So what do you mean by that? What do you mean by that? This is going to be some resistor R. Here you have some V input. But what is saying, sir? This resistor RL is a variable resistor. This RL is a variable resistor. This load resistance RL is a variable resistance. This load resistance RL is going to be a variable resistance. Variable resistance, and V input is constant. And V input is constant. V input is constant. When the V input is constant and load resistance RL is variable, still same current will flow. That is current IZ you call is going to be current load current IL. Load current IL. Right. So now what we know, sir? We know that I is equal to Iz plus IL. Iz plus IL. Iz plus IL. And the V naught is going to be IL into RL. IL into RL. Right. So now what is happening, sir? Let's say I am increasing the RL value. When RL value is increased, what happens to IL value? Because the voltage of across this must be constant, this IL will be decreasing. So when RL is increasing, for I is equal to Iz plus IL. So when RL is increasing, this Iz will be increasing. Simple, sir. When this load is increasing, the current flowing to the load will be decreased, yes or no? Tell me yes or no. When the load resistance is increasing, the current flowing through it will be decreased. When this current flowing is decreased, which current flow should be increased? Because this I is constant. When this I is constant, if this current is decreasing, definitely the current will be taken by the Zener diode. Definitely this current will be taken by the Zener diode. So as I is increasing, Iz increases, IL decreases. So as RL value is increasing, Iz increases, IL decreases. right? So then what happens to V naught? V naught, what is V naught? IL into RL. So, but what you have studied, as RL is increasing, IL is decreasing. So, V naught is constant. V naught is constant. Then what is the value of I, the total current I? Total current I is going to be VI minus VZ by R. VZ by R. So now here comes some important term, some important terminology. That is, so I is going to be IZ maximum plus IL minimum. That is what, right? Because I don't want to change this current, because input is constant. When the input is, observe this very carefully, sir. Don't get confused. Input is constant. When the input is constant, the current flowing through the load resistance, this resistance R is also constant. Yes or no? When this is constant, this is also constant. This current is also constant. But what's happening? You are changing the load resistance RL. The load resistance RL is changing. IL change, that is IL decreases. When the IL decreases, now what happens to Z current? Current increases. So at IL is minimum. When IL is minimum, IZ is maximum, because this I is constant. Let's say the IL is 1 milliamp is the minimum current. One total current I is equal to, I'll tell example, I'll tell you right here. I'll do one thing. Let I is equal to 10 milliamps. 10 milliamps. And then IL is equal to 5 milliamps. And then IZ is also 5 milliamps. So as RL is increasing, let's say IL has become 1 milliamp. When IL becomes 1 milliamp, and IZ should be how much, sir? I is a constant. So IZ plus IL, which we have, this anyway, this is 10. This IZ is plus IL is going to be 1 milliamp. So definitely IZ should be 9 milliamps. 9 milliamps. So remember, whenever this IZ is minimum, IL is minimum, IZ becomes maximum. IZ is maximum. So when IL minimum, IZ will be maximum. IL is minimum, IZ will be maximum. IZ will be maximum. Sir, when IL is minimum, what is the value of RL? This comes the story. When IL is minimum, what happens to the value of load resistance RL? Definitely RL is going to be some V naught by IL minimum. As this is in denominator, when this is a minimum, obviously you will get this is RL maximum. RL maximum. So RL maximum is going to be V naught by IL minimum. RL maximum is going to be V naught by IL minimum. So when IL is minimum, obviously RX is going to be maximum. So RL maximum will get only when V naught is going to be IL minimum. Similarly, you will get RL minimum. You can simply easily say RL minimum is going to be V naught by IL maximum. For this, do you need explanation? No. When IL is minimum, let RL maximum. When IL is maximum, IZ becomes minimum. So when IL is maximum, your IZ will be minimum. IZ will be minimum. Remember this point also. That is, IL maximum is going to be I minus IZ minimum. Only simple feel, sir. You need not worry much about this. I is equal to IZ plus IL. I is equal to IZ plus IL is the only thing you should remember. Right? All are waste of time. All are waste of time. So how will you calculate the value of? Is all something I'm trying to change from here to there and there to here. So I will calculate IL maximum. IL maximum is going to be VI minus VZ by R. That's it. That's it. So what is RL minimum? Again, RL minimum formula is going to be, this is VZ into R by VI minus VZ. RL minimum. Or RL minimum is going to be V naught by L maximum. So what you are doing is simply you are substituting here. That's it. IL maximum substituting R minimum. You substitute this here. IL maximum. What is IL maximum? IL maximum is going to be VI minus VZ by R. Simply you will get that. Simply you will get that. Okay. Yes. Yes, VZ is correct. Vasu, you got right answer. VZ should be constant always. VZ should be constant always. In the third case, we have a fixed RL value and a variable input. Variable input. So how it looks like is, just give me 5 minutes. I am trying to close this chapter topic, and so that tomorrow we can discuss problems on this. V input is varying. V input is varying. V input is varying. It's going to be R. It's going to be RL. It's going to be Z. VZ. I should say VZ. I should say VZ. Yes, it should be constant. It should be constant. We know that V output is going to be always IL into RL. IL into RL. It is always constant. It is always constant, right? So for V input is increasing. Let's say V input is increasing. When V input is increasing, I increases. This is the current I. This is the current IZ. This is the current IL. Right? When this is RL is fixed, when this RL is fixed, that current flowing through the RL is also fixed. So when I is increasing, so I is equal to, we know that IZ plus IL. This is constant, sir, no change. So when I is increasing, when V input is increasing, I increases. When I increases, IZ increases. So all the problems will be taken by the Zener diode only. All the problems will be taken by Zener diode. All the problems will be taken by Zener diode. All the problems will be taken by Zener diode. So, but the voltage across this should be constant. The voltage across this should be constant. When the voltage across this should be constant, now what will the voltage across this point will be, sir? So for a fixed V, for a fixed V naught, so this is going to be fixed, constant. So who is taking the entire burden? The Zener diode is going to be taking the entire burden. So VI is going to be VR maximum plus VZ plus VZ. That's a voltage. That is a voltage. So what is VR maximum? What is the VR maximum? So VI is going to be IR maximum into R plus VZ, because Zener voltage is constant. The maximum current is flowing, but still it is giving constant voltage. That is the greatness of the Zener diode. That is the greatness of the Zener diode. So VI is going to be IR maximum into R plus VZ. IR maximum into VZ. So if it is a VI minimum, so this is going to be VI maximum I'm talking about. This is going to be VI maximum I'm talking about. So what is VI minimum? When VI is minimum, that is we are applying input voltage, very minimum voltage. Now what we'll get is VR minimum plus VZ, because Z is constant. So in the next class, we will try to see how this calculations can be done. If you do some problems, you'll understand. If you do some problems, you'll understand all this very clearly. Okay, the next class we'll try to solve all the. I think I wanted to discuss some problems here, but the time is not sufficient. Then in the next class we'll try to discuss the problems. Hope you understand all the concepts so far. Did you understand all the concepts? Yes or no? I think you have understood all the concepts. In tomorrow's class, along with the problems of Zener diode, we'll see another beautiful, important diode called tunnel diode. Very good tunnel diode we will discuss. Okay. In tomorrow's class, we will discuss that. So this next, I'll post this in the Telegram channel. I'll post this to today's class notes. You can check the class notes. And these are the YouTube channels which we have. These are the YouTube channels which we have. We have Creatix Gate EE, that is for ECE, ECE, Triple E, and instrumentation. We have Creatix Gate. An Unacademy Gate for mechanical engineering, production engineering, and engineering sciences. Engineering sciences, and then Unacademy Gate for civil engineering. Thank you all. Thank you. So Unacademy Gate civil engineering we have. Unacademy Gate civil engineering we have. And we have engineering Pathshala. We have engineering Pathshala. Then we have Unacademy computer science. And we have Unacademy computer science for computer science and IT students. And we have Unacademy Gate questions. Unacademy Gate questions we have. And then we have Unacademy Gate Telugu, where I am teaching right now. You have parallelly aptitude classes are going on. And I think communication systems is going on. Digital is going on. And mathematics is also going on. You have electrical junction. You have electrical junction for electronic students. So you can listen to all these classes. You can listen to all these classes very carefully, right? So, but before leaving, don't forget to like the video, share the video, subscribe the channel, and press the bell icon. Don't forget to like. Please do like. Your likes are very important for me, right? Then only I can increase my flow, right? Thank you all. Bye. Good night.